Yeah, so hi everyone, welcome. I'm Carmel. I'm a software engineer at endjin, and I'm here with Ian, who is our technical fellow. We're going to talk about a project that we've been involved in for about 5 years, but as Ian will discuss shortly, it's been around for a lot longer than that. But for those of you that may have missed the announcement, last month, well, 2 months ago on the 18th of May, Project Reactor went live. So the code which supports the running of the project is now open sourced. It's under an MIT license, which means that it's free for commercial and non-commercial use. And we also launched the reactive.net site, which it has a detailed history of the project, loads of documentation, some talks, demos, and blogs. But I guess quickly it's just worth kind of discussing who is this for. So Reactor is a stateful, reliable, and distributed processing platform, stream processing platform. And we've spent quite a lot of time over the past few years kind of thinking about what exactly is a reactor-shaped problem. Reactor extends reactive extensions, or RX, which are a really good feature of .NET, which are built around reactive query processing. And Reactor evolves that reactive model to allow you to do reliable and long-running queries using persistent storage. And these stateful queries, they can survive restarts, maintenance, unpredictable failures, and even complete machine migrations. So using that durability and reliability, you can run queries that can last for days, months, or even years. But it also allows you to stream a huge volume of data by distributing the processing, and can stream this data incredibly quickly and simultaneously run like a huge number of queries. But yeah, so using this technology, we're able to continuously analyze large volumes of data over a really long period of time and execute loads of queries simultaneously. And it can do this really efficiently to the point that the entire platform can be run on a Raspberry Pi. Some of the use cases that we've been talking about over the years have included telecommunications, IoT sensor analysis, tracking of like vessels, so where vessels are in the ocean, which we'll talk about a bit more in a bit, and personal assistant technologies like Bing Cortana. But we're really excited to see, now that it's been open sourced, what else the community can come up with. But without further ado, here is the reactive.net site. So from the home page, you can navigate to a sort of introduction to the project. You can download an ebook, which delves a lot more into the history of the project. And you can sort of go into more detail in a load of different topics using different blog articles. There's also some demos, blogs and talks, which are produced to try and go into more detail on various parts of it. You can look at the different levels of Reactor. So Nucleon contains the kind of low-level primitives, which the system is built around. Reactive is the layer on top of those, which kind of mirrors a lot of the stuff that is in classic reactive extensions. And then Reactor is the platform which is built on top of reactive, which allows you to do this long-running and stateful processing. You can also, there's links to a series of demos. So if you click on one of these, you end up in the Reactor repo. So these demos are .NET Interactive Notebook based. I think saying Diego Colombo is doing a talk. So he's been working on .NET Interactive Notebooks. Sorry, my internet. But yeah, so these demos are based entirely on .NET Interactive Notebooks, and hopefully this one will load. But Ian's going to be going through these notebooks in a bit more detail, or some different versions of this demo in a bit more detail later on. But this specific demo is based around displaying vessel shipping data on an interactive map. But I don't know why it's not loading, but we'll see that in a bit later on anyway. But all of the code in this repo is the stuff that's been OSSed. So this contains all of the all of the platform which has now been open sourced. And so this is the code which underpins much of Bing Cortana, which is Microsoft's digital assistant technology. And the journey to getting it all open sourced has been quite a long one, but I'll let Ian talk about that in a bit more detail now.
Okay, so if you've been following .NET development for some time, then you may already have been aware of Reactor for quite a few years now, because Microsoft has been talking about it in public for almost a decade. So Microsoft's got this website they call Channel 9, where they record interviews with employees, mostly engineers. And fairly early on in Channel 9's history, they did an interview with Bart de Smet. So Bart de Smet is a principal software development engineer at Microsoft, and he's basically the brains behind Reactor. You may have spotted his avatar there on GitHub when Carmel showed the repo briefly. And so Bart, in these interviews almost 10 years ago, presented a vision for how the basic principles behind the reactive extensions for .NET could be extended into a service platform for the persistent, reliable, long-running, and highly scalable event-driven processing for the kinds of applications that Carmel's just been talking about. And back then, he called the system Reactor, although it was spelled with a C back then instead of a Q. Well, we'll get on to why it has a Q later on. So Reactor was actually always a central part of the vision for the reactive extensions. So although RX, the reactive extensions, have been widely adopted in the years that followed, not just in .NET, but there have also been ports to other languages, the RX libraries that we have today were really only ever meant to be just one piece of the jigsaw. So, as you might know, RX originally emerged from a group at Microsoft whose remit was cloud programmability. And the RX libraries that came out of that group that we use today work within a single process boundary, but they were designed to provide a well-founded representation of how streams of information could flow between multiple layers of an application that could be distributed across many computers. Now, if you saw those early sneak previews in those Channel 9 videos, and if you're anything like me, then you would have been disappointed that they weren't followed up later with the publicly available release. And you might even have assumed that the technology had simply been abandoned, but actually it wasn't. Many groups inside of Microsoft have been using it for many years. So initially it was deployed as part of Bing Cortana, so that's Microsoft's digital assistant. And in that first application, they proved scalability. So they demonstrated it was able to support tens of millions of concurrent, persistent queries. And it's the thing that enables Cortana to give you notifications under certain situations. So for example, if you ask to be notified when a change in traffic conditions means you've got to leave early to get to your next meeting on time, that's using Reactor under the covers. But it's not just in that. Office 365 also uses Reactor internally in a variety of services that need to respond to changing information from a variety of sources. So this technology has been successfully deployed at very large scale inside of Microsoft. But for a variety of reasons, the team behind it never managed to find a way to get it out into public hands. However, about 4 years ago, Endjin, which is where Carmel and I work, Endjin approached Microsoft to see if they would let us use Reactor. Because we had a customer who operates a broadband network, and they needed to do intelligent monitoring of literally millions of devices. And we'd heard about this Reactor thing on Channel 9 and thought, well, that seems like it would be a great fit for the application we've got, because we wanted to be able to have millions of concurrent but individual monitoring queries. We wanted to have every single customer on this broadband network essentially getting their own private monitoring logic, but in a way that could also take into account system-wide state, like whether the local exchange has got a problem. Because with this sort of application, what you want to be able to do is distinguish between a customer-specific fault and a fault that's somewhere else in the network. Because what you don't want to do is dispatch 20 engineers to 20 different customer sites when the problem is actually that the telephone exchange is on fire. You need to understand where the problems are, and Reactor gives you this kind of local and global universal view that makes these sorts of things possible at that kind of scale. So the goal was that if we, Endjin, could demonstrate that it was viable for people outside of Microsoft to use Reactor, then they would try and work out some way to make it available. So internally, we built various systems that host Reactor up in Azure, proving that it can be used outside of the very, very specialized hosting environments that Microsoft have for things like Bing and Office. It's taken a while since then to get everything lined up, but thanks to a huge amount of effort on Bart de Smet's part and also support from the .NET Foundation, now the code for Reactor is out there under, as Carmel said, the MIT license, so anyone can use it. Now, it is worth us just being clear what hasn't been made available. So to host Reactor, you need to provide it with some sort of environment that provides it with various quite specialized persistence and communication services if you want to be able to scale out to millions of queries. And Microsoft couldn't share their implementations of these persistence and communication services because they are very specialized to the particular environments they're running in. So what you won't be able to do is download the repo, build it, and instantly deploy it somewhere to have an industrial strength service running in minutes. And part of the reason for this is there's many, many different ways you could do that. There are lots of trade-offs about how you can host it. And you don't necessarily even want the scale. You might not want the complexity that goes with the scale, because you can just host an isolated Reactor instance on something very small. Like Carmel said, you can host it on a Raspberry Pi, for example, which is a very different sort of an environment from a cluster with hundreds and hundreds of servers. So the bits that are available in the repository that we'll be looking at in a bit later, they're more of a toolkit from which you can build all sorts of different kinds of Reactor deployments. And because Reactor has been used in numerous environments and deployed in many different ways over the years, it's seen a lot of extensive refactoring, which makes it very flexible, but it also makes it a little tricky to approach the code base. A few of the people who've tried to look at it so far have struggled to find a way in because there's very many different ways you can assemble it together. So I will later on be showing you some of the demos in the repo, but they are a little bit complex for that reason. So before we get to that, we've got some demos that provide an easier way into understanding how it works, and then we can show you some of the complexity once we've got past the basic principles. So at this point, I'm going to hand back over to Carmel, who's going to talk about the fundamental programming model that underpins all of Reactor, which is reactive extensions, or RX, as they're usually known.
Yeah, so clearly, in order to be able to understand Reactor, we first need to take a quick look at classic RX. And the underlying concept behind RX is the representation of streams of information. And I think the easiest way to describe it is by comparison with a collection. So in a normal collection, you have a set of values, and when you want to read the next one, you go and ask for it, usually by iterating through the collection. So this is a pull model for processing data. But in RX, instead of a collection, you have an observable. And instead of iterating through it, you subscribe to it. And this tells the observable that you want to listen to any values that it produces. So this is a push model, where instead of going and asking or pulling items from the collection, they are pushed at you whenever they're ready. And you subscribe to an observable using an observer. So observables have a subscribe method to which you pass an observer. And so this tells the observable that the observer wants to listen to these values. And when an observable produces a value, it will pass that value to the onNext method of any listening observers. Once the observable has finished processing, it'll call the onComplete method to any observers that are subscribed, and this will tell those observers that it won't be producing any more values. Or if during processing and the observable produces an error, it will call the onError method of each of the observers, which will notify the observers that an error has occurred. There are two different sorts of observable, a hot or a cold observable. And a hot observable produces values whether or not anything is subscribed. So this means that if nothing is listening, these values will be lost. So this is kind of similar to old-style TV broadcasting, where if you didn't catch a program when it was on, tough, you've missed it. A cold observable doesn't produce values until something subscribes. And so this is much more similar to the more classic on-demand TV, where you just go and press play whenever you're ready. So when you're using RX, you're able to represent streams of information as and when that information is available. And this type of reactive data processing opens up really exciting possibilities for streaming and real-time processing of data. And Ian's going to take us through a vessel tracking-based example.
Okay, let me just share my screen. So, before I show you the code, here is a program which is showing some events. And this is some real live data that I'm going to use as the basis for the demo I'm about to do. So as I'm sure you've already inferred, all of this is information telling you where ships are around the coast of Norway. So there is a publicly available service which is hosted by the Norwegian government that makes available information about shipping around the Norwegian coast. So as you may or may not be aware, pretty much all ocean-going vessels, all vessels above a certain size, have to have certain equipment that reports the location, the heading, the speed, all sorts of information about where the ship is, where it's going, what its final destination is, and so on. This system is called AIS. It's the Automated Identification System. And it integrates with some sort of global positioning system, sometimes GPS, sometimes GLONASS. They support a number of different ones. But basically, the ships need to know where they are and to be able to say what they're doing right now in order that you can navigate safely around them. And this is what the actual raw radio messages end up looking like. Well, technically, they're not in ASCII, they're in binary, but this is the ASCII decoded version. So what you're seeing here is a mixture of two kinds of messages. If I quickly just suspend this, you can see that the ones I've colored in green have the names of ships in and a few other pieces of information, and everything else, probably less obvious, but everything else basically has location and speed and direction information in. And these are broadcast as separate messages. And this is going to become interesting and relevant when we start to try and process this with RX. The reason that the ships send their location and speed separately from things like their name and their dimensions is that ships don't change their names very often, and they generally hope not to change their dimensions at all, whereas they do move around quite a lot. So in order to conserve bandwidth, and the radio bandwidth is quite scarce at the frequencies that they broadcast on here, they only send information about their names every few minutes, whereas they send information about their location often several times a minute, more frequently when they're moving more quickly. So we have these streams of information, and this is all coming from, as I say, a server in Norway. So with that in mind, I'm now going to go into a notebook that uses this stuff. And so we could see how we might use RX to process information streams of that kind. So the first thing we're going to do is just load up a couple of NuGet packages. So I'm using a .NET interactive notebook here. And as Carmel mentioned, you're going to be hearing all about these from Diego in a few weeks' time, who works on the .NET interactive team. But we love them at Engine. We use them for all sorts of things. So this is a C# based notebook. I'm just going to bring in a couple of NuGet packages, if it will let me. Did that do anything? Right, looks like I'm going to unload this and reload it because that's been sitting there for several minutes now and seems to have got confused. Okay, why is that not running anything? That's not a good start. I'm going to quit this copy of Visual Studio and restart it. Okay. That's not Visual, that's VS Code I want, isn't it? Right, let's try this again. So, okay, that's quite disturbing. I even tested all this earlier. Why has this suddenly stopped working? Ah, now, finally, it's working. It was just messing with me. Right, so these NuGet packages, these are libraries that Engine actually maintains. So we've written some high-performance, high-volume AIS processing code as a result of a project we did last year for tracking vessels and trying to detect illegal fishing activity. So we wrote these libraries that are now open source and available for use up on GitHub to process in AIS messages of the kind that you just saw. So let's bring in some namespaces to work with those. We've also provided a class that's able to receive messages from that Norwegian service. So that's the actual IP address of the service that provides the data you were just seeing in that console app. So I'm going to run this thing. It doesn't actually start listening until we tell it to. And then we wrap it in this thing. And this is where Rx starts to come into the picture. This receiver host class sits around this network stream receiver and presents all of the messages as an observable stream of information. So we can then start to use Rx to process those messages. So what on earth could we possibly do with a stream of data telling us where a bunch of ships are? Well, obviously, we're going to show them on a map. So I am going to load up a copy of Bing Maps. So, oh yeah, .NET Interactive Notebooks let you have a mixture of different languages on your page. So this is an HTML cell rather than a C# one. So this one, I've been able to load up the Bing map. So I am going to zoom in on Norway because that's where all the data is going to appear. So nothing's running yet, so we can't see anything, but that's ready and waiting. So we need to do a few things to connect that map up to our data source, because that map is an HTML thing. It's running up in JavaScript land, and so we need a way to communicate. And .NET Interactive makes this possible. Actually, it makes it possible because Endjin submitted some code to the .NET Interactive team, and they kindly agreed to merge it in. So this sort of thing has become possible. It is possible now to send commands, custom commands that you can define from the .NET bits of the code up into the JavaScript piece. So here I am defining a .NET type that describes the shape of the command I want my C# code to be able to send up to JavaScript. So in this case, it's basically the position of a vessel, the direction in which it is moving, which is not necessarily the direction it's pointing, its unique vessel identifier. I think I can never remember what MMSI stands for. Mumble something identifier, and the name, and of course we're going to cut other things in according to what type they are. So we declare this type of command, and we also tell .NET Interactive that we intend to send commands of this type up to the JavaScript kernel, and this does a bunch of serialization handling, so it knows how to send these messages back and forth. So that's going to enable us to send the messages, and then up in the JavaScript side, we just register a handler saying anytime something sends us a command of this kind, we're just going to invoke a function on the map that updates the position of the relevant vessel. So that's my connector up from .NET into the map. So then what are we going to do? We're going to use the stream of the observable stream of messages describing the vessel location to paint the map. But before I talk about this code, I'm going to show you a pictorial representation of it because it's a little challenging. So the AIS feed, which you saw the raw data from in that console app, as you saw, provides a mixture of different messages and message types. Each message that we get will be concerned with some particular vessel. So they all have an ID, an MMSI, identifying the particular vessel that the message is coming from. And some of these messages will just report location data. And then from time to time, each ship broadcasts what it calls static information, which includes the vessel's name, its dimensions, and a few other things that generally don't tend to change very often. But we don't get those all the time. But obviously on the map, we want to paint everything. We want to paint this vessel is called this, and it's this type, and it's here. So we want to somehow combine these things together. So we've got this stream where it's like everything's jumbled up. So how are we going to get some sort of uniformity with this? So we're trying to get to a combined name and location stream. We want our messages to say the vessel called this is here, the vessel called that is there, and so on. So here's what we do. The first thing we do is we take our stream of data and we group it by vessel ID. So Rx supports most of the standard link operators, and that includes group by. You can tell it to group data by some particular criteria, and we're going to use the MMSI, the vessel identifier. And what you get when you use grouping in Rx is a observable stream of observable streams. So each time the IIS feed produces a message from a vessel we haven't seen yet, the grouping operator will actually spit out a new observable sequence. I've only got 2 on the page here because that's all that will fit. But obviously in practice, we'll have hundreds or thousands of these things as the number of vessels that we've seen goes up and up. So we split the data by vessel. And so now each individual stream is concerned with just one vessel. And so we've got messages of different type. And that's the next thing we do is we discriminate by type. We say, okay, for this vessel, 1, 2, 3, 4, there are the location messages. and there are the name messages. And what we want to do is take the latest of each and combine them together to get all the information. And we can do that. There is an operator built into Rx called combine latest, and you can feed in any number of source streams, and it will produce one item containing the latest item from all three streams. So when we split the group up into location and name messages and then combine those with combine latest, here's what happens. When the first location report comes along, nothing happens because we've only got the location. We don't have the name yet, so combine latest actually can't produce anything. Same happens when the second location report in this example comes along. But then we get the name for the vessel, and now we've got both pieces of information. And so it can emit the combined name and location. And the same thing's going to happen down with the second vessel here. Once it's seen one of each kind, it can emit the name and location for that too. And then for these two vessels, we're good to go. We've got all of the kinds of messages we want. So as they go on to produce more messages, we can keep producing the combined latest name and location. And then we can do a select many to flatten that back down into a single stream. And again, it's the same select many operator that you can use in things like link to object or link to SQL. That basically takes multiple things and squishes them back down into one thing. So we get what we wanted, a single stream where each message reports the name and location of a particular vessel. So that is how it's going to work. So now let's look at how that's actually implemented in Rx. So remember, we have this receiver host, which is providing an Rx-shaped source of messages on top of our Norwegian data observer. And then we run that through Rx's group by operator, telling it we would like to group by unique vessel ID. And this gives us an observable of grouped observables. So this is our observable of observables. It's a special kind of observable, the child one, because not only does each of these things produce a sequence of AIS messages, it also tells us the thing it was grouped by. So that's the MMSI there. So we basically get a bunch of groups. And then we can do exactly the processing I just described on the slide. So we take the observable groups, and then we take each message within that group and we split it up by type. So I'm saying, okay, for the per vessel messages within the current group I'm looking at, give me all of the messages that concern navigation data. So that is location, speed, heading over ground, actual heading, and all those sorts of things that tell you which direction the ship is going and how fast it's going and so on and where it is. So that's vessel navigation. And we also identify all of the vessel names in a separate stream. And actually, I didn't show this on the previous slide, but there's actually a third type here. We're looking at the ship type. Is it a tanker? Is it a passenger vessel? Is it some weird experimental wing and ground machine? And we're going to use that to determine what color to paint the thing on the map. So these are the three streams, and this happens within each group. And then we use combine latest to say I'd like to take those three streams and I'd like to produce a single stream that contains the latest value from all three of those. So now we've got this, for each group, we have a single stream called vessel locations with names, and then this second from does our select many under the covers, if you know your link expressions, and this will flatten everything back down. And then finally, this enables us to produce a sequence of messages where we say, well, here's the MMSI that actually comes from the group key, and then here's the navigation data, the name data, and the ship type data. So we get this stream with everything in it. So I'm going to run that. It won't do anything yet because Rx doesn't actually start producing messages until you subscribe to a stream. So we've still got a thing that has the potential for producing messages yet, but it's not doing anything until I tell it to do something. Then we color everything in. So we'll use that in a second. And here we're actually going to subscribe to that unified source. So we call the subscribe method, passing in a callback. So this is going to get invoked for every combined name and location. So we just destructure that back out into its component parts. This thing's a tuple. We're just flattening it back out into all the different pieces. And then we use that to build this vessel position command, which remember was the thing I'm going to send from C# back up into JavaScript land so that it can ultimately be painted on the map. So we're going to give JavaScript the latitude, longitude, course over ground, all the information about the ship, and we're going to color it in. And so At this point, we've subscribed, but actually we're still not running because our receiver doesn't actually connect to Norway until we tell it to. So when I click this one, now we're live. So if I scroll up to the map, look at that. Ships are starting to appear. Now, it's 3 right now, 4, 5. There's probably more than 5 ships around Norway right now. This is taking a little while to appear because, remember, we're relying on this combine latest functionality. So the data is streaming in at speed from all these ships, because there's a lot of them and they're all reporting the location fairly frequently. It's all coming in, but we can't show anything on the map until we've actually seen both location and name data and type data for every single vessel that there is. So gradually the number of vessels gets higher and higher as we start to see all the data, and it's getting a bit of a mess now. So let's zoom in a little bit. Let's see what's happening around Oslo, shall we? There are probably more things there. The longer you leave this to run, the more things start to appear, and eventually you can start to see them move around. But so I'm not going to sit and stare at a map for ages though, so let me just quickly shut that down. So this lets us tell the receiver to stop. So that was the RX demo. So we've not used Reactor at all yet. So I've hit the wrong button. You think I'd know by now, I've been teaching for this long, that you should hit Shift F5 when you want to do that, but no. Right, try again. So what does Reactor add to the mix? Why do we need Reactor if I can do all that? Well, there were some issues with that using plain old RX, and the most obvious one was the fact that it took a while for the map to fill in. So data was streaming in all the while, but it took a long time for it to build up the state that it needed to provide a complete picture. The longer I left it, the more ships appeared. And here's the thing. If you shut it down, you kind of lose all that state. If I go back into this notebook, if I just close the notebook and then reopen it, we're kind of coming in from scratch again. So if I click Run All, is it struggling again? Right, okay, I'm not going to do that. .NET Interactive updated itself just before I started this evening, so who knows what's going on there. You saw it run, but the point being, it's lost all of that state. All of the information it was building up in that query, all the grouping, all the associations between the different vessel types and their names, all that information being held by the combined latest operators was just being held in objects in the process that C# code was running in. So when you shut it down, it all goes away again. Every time I restart the notebook, I'm going to cause massive disruption. Now, for a demo like this, that's not a huge deal, but it is a problem if you wanted to provide this as a long-running service. So if you wanted to provide some sort of online service that provided this combined stream of information all the time, then you would not want that sort of disruption. And here's where you start to run into problems using classic RX. You can build services like this, but if you need to restart a server for any reason, or if you just need to move off one server onto another one, you've got a bit of a problem, because this happens all the time. We need to take servers out of service so we can install updates to the operating system or update our application code. We can't just have things running forever. So how do you move the information between servers in RX? Classic RX does not provide a way to store persistently the state that builds up inside one of these queries. And this is one of the things that Reactor brings to the party. It provides the ability to walk an entire subscription, like that one we had there, find all of the state and write it out into a serializable form so that it can then be reinstated somewhere else. It makes it possible to essentially teleport a complete RX query from one place to another. Now, actually, part of what makes that possible is a technology called Bonsai, because one of the things you need to be able to do to make that work is move actual expressions around from one place to another. Because again, if we examine the code I was just looking at, this query here, there are bits of code in here that just end up doing sort of C-sharpy things. So this is some code that's building up a tuple, for example. That sort of thing needs to be able to be sent across the network if my query is going to be able to move from one thing to another. So it's not just the state of the subscription, it's actually also the description of what the subscription itself looks like. So there's also serialization of expression trees. And if you've watched the original Reactor demos from way back when that Bart did 10 years ago, you may have heard the term Bonsai. Bonsai is the name for the technology that enables this. A Bonsai tree is essentially a .NET expression that has been serialized so that it can be moved from one machine to another. And this serializability of expressions and of the state of a subscription doesn't just enable us to migrate from one machine to another, it's also what enables reliability. So what happens if a machine stops running when we weren't expecting it to, before we've had a chance to actually migrate everything off it? Well, in that case, the way Reactor has of dealing with that is partly that a Reactor service regularly checkpoints all of the subscriptions that it has running. So if something does crash, it's got a fairly recent copy of all of the state. And then it relies on the fact that the RX processing model is essentially deterministic, and there's mechanisms for replaying messages that came in after the last checkpoint. And also on the egress side of things, there are mechanisms for making sure that you don't send duplicate messages out. And so those things in combination are what enable the reliability that Reactor builds on top of RX. So these are the things that the RX doesn't have, that Reactor brings to the party, that make it possible to build reliable, distributed, long-running processes. It's because of these things that Microsoft has literally had queries running for years, like 8, 9, 10 years or more. Not more than 10 actually, because it hasn't been around that long, but almost 10 years in some cases, queries running up in services that they've had running all that time. So on that, I'm now going to hand back to Carmel, who will show you some of this, how it actually works in practice.
Yep. So yeah, one of the, as Ian was saying, one of the big things that distinguishes Reactor from classic RX is this ability to run long-running and stateful queries. But what does this actually look like in practice, and what does it mean to store the state of a query? And use the take operator as an example. So say in classic RX, we use this operator to take the first 8 items in an observable stream. We're assuming that the stream acts like a queue, where items are processed once and then removed from that queue. And in normal RX, if we apply the operator to an observable, we would just take the first 8 items in the stream. However, if you restarted the process and then reapplied that observable to the stream, we would again take the first 8 items. And this would mean that all of the state from the items that were previously processed would be lost, and that the first 8 items from somewhere partway through that stream would be processed. When using Reactor, operator state is persistent. So as Ian was saying, the reactive engine generates checkpoints regularly, and these checkpoints record where in the stream you've reached and what the state is of the operator at that point. And this means that should the engine be restarted, you can restart processing from where you left off. And not just this, but the preserving of the operator state means that these operations, such as take, won't be reapplied. So we're going to look at a quick demo of how this works in Reactor. So here I've got a 2-part demo. When I run this, we'll either run part 1 or part 2. So if we look at part 1, we first recover the state of the query engine, and at this point, no subscriptions have been started in the engine, so when it starts, nothing will happen. But we then get a reference to the timer observable definition. So this is an observable that just produces a value at a given interval. We also get a reference to the console output observer, and this is an observer which, when something is passed to its onNext method, it writes it out to the console. And so using these definitions, we can build up our current speed observable. So this just takes the timer observable that produces a value every second, and then so each second it will produce a value using this getSpeed method. This getSpeed method in this very simple demo is just producing a random value which could represent the speed of a car, but this could be anything. This is where you might go and read data from an IoT IoT sensor, or you might process an event from a telecommunications device. So basically, this is where you input data into your system. And then we will take the first 8 items of the observable. Nothing will happen at this point. As Ian was saying, this is asynchronous process definitions, so nothing actually happens until something subscribes. We then subscribe our console output observer, wait 4 seconds, and then checkpoint and unload the engine. So if I run this code, we can see that the first 5 items are passed to the onNext method of our observer. The engine is unloaded and the state is saved. And if we look back in the code, we can see that this state is being written out to disk. So I'm not going to switch over to part 2 of the demo. So in this example, I'm going to run part 2 on the same machine, but this state has been persisted. So this could be run on a totally different machine, and just the engine could recover from that state. So again, in part 2, we run a recovery, but this time something has happened in the engine, so we won't start from scratch. But if we run this code, we now see, what's it spelled? Slow. We will see in a second that the next 3 items are passed to our observer. The onComplete method is then called, and then the engine is unloaded. So, unlike in regular RX, the state of the take operator has been saved, and instead of restarting and taking the next 8 items, it remembers that it has already taken 5 and just produces the remaining 3. So the processing continues as if the restart had never happened. And the fact that these queries can run continuously through engine restarts means that you have the ability to support extremely long-running operations. And these queries can move between separate processes and machines, and the state of the process is written out to persistent storage. And as Ian was saying, Reactor also gives assurances about reliability that mean that you can be sure that no state will be lost throughout these restarts. So you can run RX-like queries, but with predictable and repeatable results. So the upshot is that you can create extremely long-running queries without worrying about engine restarts producing unpredictable or just completely incorrect results. And so it's this technology that is used to power the long-running queries that are needed in things like Bing Cortana. So Ian is going to run through a slightly more exciting demo, but first I think we're going to take a break.
And then move that away. Okay, so now I'm going to show basically the same sort of information processing, but this time we are actually going to use an instance of Reactor hosted as a service. So this happens to be running locally, so we typically would host our Reactor service in Service Fabric up on Azure, but I want to be able to show you a few things happening inside Reactor through the debugger, so you can see some things about how it's working. So we're going to run with a local debug instance. So let's hope it's going to talk to me now. Okay, good. The notebook's working now, which is good.
I don't think you're screen sharing for me. I don't know what it's like for everybody else.
It says you're sharing the screen.
It says you started screen sharing, but it doesn't actually show you.
Oh, I'm sorry. Let me. Okay, I'll try again. So, screen 1, share.
Yeah, there you go.
So,
it's working.
Okay, right. So the little widget thing appeared last time as well, but clearly it was pretending. Right. Okay. So I'm adding in some NuGet packages. You'll notice things like gRPC and protobuf and also Reactor client. So this is because we're going to talk to an outer process Reactor service. So like I say, it could be hosted up in Azure, but this one is actually running locally, but we're still talking to it over a network. So this is more Reactor as it's typically intended to be used. So far we've been showing you stuff in memory because that way you can observe what's happening, but this is now a slightly more sort of real setup. I'm just going to print out the process ID that this C# code is running in, so we can sort of compare what's happening where. If I quickly bring over my task manager and sort by PID 57848, it's that .NET process there. So there's basically a .NET.exe process spun up by the .NET Interactive Notebook infrastructure that hosts the C# code we're running here. So I'm going to bring in a bunch of namespaces and also some stuff specific to our engine implementation, our Reactor implementation. And because I'm talking to just a locally hosted implementation, I'm just running with all authentication turned off because it makes the demo simpler. So the critical point of this code, though, is this thing here. This is the thing we actually want. It is a remote reactive client context. And this is sort of the Reactor equivalent to something like a DB context or an object context, those sorts of things. It is a thing that you have in your local client process that allows you to do things to the service remotely. So whereas an entity framework context lets you get hold of tables and execute queries on those, a reactive context, which is what the base class of this thing is, gives us a way of talking to a reactive service and doing things with observable sources and observers that actually run inside that service. So this is essentially a way of getting hold of, if you like, avatars that represent subscriptions and sources and things that are going to run elsewhere. So what next? Now, because everything's going cross-process, interesting questions of where do our types live start to come into play. If I want to have something a bit like the vessel command I had earlier, which represents all the different properties I am interested in, well, now I've got a slight problem because my class is defined here in the notebook, but I need to be able to run a query in Reactor running as a service. And I don't particularly want to have to try and compile a DLL and deploy it to both of them. So Reactor has this thing called the data model, where you can define what are essentially structural types. So here I'm using a C# class, but I'm annotating it with attributes where I give every property a URI. And when you do this, the Reactor client will let you use locally defined types. Normally, if you just define a custom type and try and pass it through this context, it will complain saying, well, that's not a recognized type. I'm not going to let you use that because that won't be there on the server. But if you annotate it with this, what it actually does is it strips off the type name and just says, okay, this query wants to read the property whose name is this thing here and this thing here and so on. So this gives us a way of defining the structure of the information that we are working with in our queries in a way that doesn't rely on both ends of the connection actually having access to the same .NET assemblies. So that's what this is about. This is a way of defining the data model we're working with in a sort of decoupled way. So next, we need to identify a source of objects. Oh, which reminds me, there's a thing I should have done before I started this demo. Pay no attention to the man behind the curtain. Right, so that is a thing that's going to read data out of the Norwegian data source and feed it into an event hub that our service is listening to. So the way we're going to do this is the event source in this demo is actually going to be an Azure Event Hub. So we have in our Reactor implementation the ability to get hold of observable sources of events that come out of an event hub, and we identify these things by URI. So earlier I basically set the system up so that this URI identifies a particular partition on a particular event hub up in Azure, so everything's all just sort of set up. This name just refers to that, and then I can pass that in to the client context object's getObservable method. So I can call getObservable, passing in that URI, and I get back an object that represents the observable source that reads events out of that event hub partition. It is still an observable source of AIS messages, but you'll have noticed the types have all grown a bit hairier. So it's actually an observable source of event hub notification of AIS message, because these things are coming out of event hubs. So this source actually gives you all of the details that come out of the event hub side of things, as well as the raw message. Actually, for this, I don't care about that at all. So I actually run it through a select statement that says, just give me the body. So we end up with just an observable source of AIS messages, which is what we actually want. So basically, I'm just stripping out the data from inside the Event Hub notification here. Now, if you're watching my screen, you'll have noticed that I'm choosing to pronounce that as observable, whereas it's quite clearly I async reactive observable. What on earth is that about? Okay, so there's various things going on here. Logically, this is just an observable source. Logically, this is just a thing that represents a sequence of events coming out of something, an event hub in this case. Why is it observable rather than observable? Well, the Q signifies the fact that this thing doesn't really exist in the process that this code is running in. It's something that exists somewhere else. And the distinction here between an I observable and an I observable is exactly the same as the distinction between an I enumerable of T and an I queryable of T. So if you've done anything with entity framework or even linked to SQL before that, you will know that I queryable gives you a thing that logically represents a collection of things, but it's typically remote. And when you run queries against it, when you actually try and execute those queries, it ends up invoking a query remotely. So if you're using entity framework, it will take your link query and convert that into SQL, send that SQL over the wire, the SQL server or whatever then executes it and then sends the results back. So this is a very similar concept. It's saying, well, this is an observable sequence of objects, but it's not in your process. It is a thing that lives on the server in just the same way that a database table in a SQL database also lives on the server. And the Q signifies the fact that when we pass in an expression like this, it's not actually going to compile this into a local method. If you look at the select I'm using here, which is scrolled off the edge of my screen, so you can't see it, but you would see it doesn't expect a func of AIS message, a func of input to output. It expects an expression of func of inputs to output, which means that when the C# compiler gets to this bit, it doesn't generate just a simple method to represent that lambda. It actually generates a description of what the lambda looks like. It actually creates an object model that says, well, this is a lambda. It's got one argument called E, whose type is whatever it is, one of those. And the body of the lambda consists of a property access, where the E is the thing being accessed and the name of the property is that thing. It builds a description of the expression that you've given it. And the Bonsai mechanism I discussed earlier is able to take those things and actually send them over the wire. So this essentially, the Q part of this means that this is a remotable observable. So it represents a remote thing. And that's one of the key things about Reactor, is everything can be done at a distance. It's also, by the way, why there's a Q in Reactor and also reactive and also Nucleon. The Q is kind of a nod to this. And by the way, there's been an IC observable around in .NET like forever. The system.reactive components have been defining this for years now. It's just that you couldn't really do a whole lot with it. So that's the Q. What's the reactive bit? The reactive bit essentially tells us that we are in the world of Reactor rather than normal RX. Why does this not have a Q? I don't have a good answer to that because we forgot to rename it, I guess. But this thing, one of the key things about I something reactive observables or I something reactive observables is that the subscriptions are actually examinable. It is possible to write code that walks over the structure of a subscription and do things with it. And this is critical for things like the ability to generate checkpoints and to serialize out the state of the subscription. That is enabled by the fact that, unlike regular RX, where the only thing you get back is an iDisposable, when you subscribe to one of these things, you actually get back a thing that has some sort of a structure to it. So that's the significance of that bit. And the IAsync bit, well, that means all of the methods that we have for things like subscription are awaitable. They're async form. So basically it looks just like the normal version of this, except everything is an async thing and returns a task or something of that kind. So logically, it's still an observable, but it's one that is remote, it is one that is reactor flavored, and it is one that is asynchronous. So let's run that. We now have a source object, and this is essentially just kind of an avatar in exactly the same way that if you retrieve a table object from Entity Framework, it doesn't do anything to the server until you start asking it questions. We could do the same thing for our observer by the way. We're not going to do this today, but typically if you're doing this sort of thing, you might use something like Event Grid to get your output out of the Reactor engine and into the outside world. For the purposes of this demo, though, I want to be able to show you things inside the debugger. So we're actually going to use a more specialized observer, which just dumps things to our diagnostic logging output. So I'm going to use this instead. But in a more realistic program, you'd do something like this, and then you connect the event grid up to, I don't know, SignalR or whatever it is you want to then go on and process the things with. So we have our observer bull, observable, strictly speaking, that represents all our AIS messages, and an observer, which in this case is just going to dump things out to diagnostic logging. And now we can build a query, and this should look kind of familiar. So we've got our source of AIS messages, and the first thing we do is group them by the mumble mumble something identifier, the unique vessel identifier, to give us our observable sequence of grouped observables. So we get an observable sequence of observable sequences of AIS messages. And the only thing that's really different here is all the extra verbiage. It's an async reactive observable, but it's still logically the same thing. So as before, we take each of the groups that comes out of this thing to get our per vessel messages, and then we split those up by type. We say, give me all the ones that are navigation data. So remember, that's the location, the speed, the heading, and so on. And also give me all the ones that are the name of the vessel. You'll notice the query has changed shape slightly. For various reasons, we're not pulling out the vessel type here because we're not going to use it in this query. And we've chosen to structure it ever so slightly differently just for efficiency purposes. But logically, it does the same thing because we've got a combine latest here that says, okay, combine the latest location per vessel with the name per vessel, and then we flatten that back out into the vessel ID, the navigation data, and the name as before. And then we have a stream of vessel positions where we have the latitude, longitude, course over ground, vessel ID, and name. So exactly as before, this is basically the same data we were feeding into the map, except for we're not coloring things in anymore because this particular demo doesn't actually paint things on a map. It's going to show stuff in debug output instead. So let me run this. So again, I've got an async reactive observable out of this. Again, this is just an avatar. We haven't connected to the service yet, actually. We've still got a client-side description of what it is we would like to do. To actually kick things off, we need to make a subscription. So we need to take the string we've got and subscribe to it. So what we're going to do here is quickly turn it into a sequence of strings because this is the structured data, and our observer in this case only knows how to observe strings. So we're going to quickly run that through another select statement that runs it through a string.format to just turn that into the information that's embedded in there. So then we can take that and we can subscribe the logging observer to that. And at this point, we should have a subscription. So when I do this, everything will take a little bit longer because this is now actually going and talking to my service, which is running in the debugger. So it's going to be rather slow, but it's done. It's given us back a subscription ID, which .NET Interactive has chosen to show as a bunch of properties, but that's the URI there. So that identifies our subscriptions. So what does this mean? Well, now I am going to go into, if I can find it, the right copy of Visual Studio. So this is Visual Studio, and you cannot change the font size on this particular window. So what I'm going to try and do, if it will let me, is, too slow. Let's try that again. Right. I'm going to use the killer application in Windows, Paint. If you're wondering why I'm not using a zoom in tool, I found it does not always interact terribly well with things like zoom. So this is one piece of diagnostic output from the query we just created. So you can see the message line at the top. MEA, that's the vessel name apparently, and that's its latitude and longitude. That's where it is, and that number there is its unique vessel identifier. Now, the reason I wanted to screen grab this and zoom in on it is to show you some of the other information. So this is other stuff that we collect in our diagnostic thing. And in particular, I wanted to highlight the process ID. So the process ID here, in which this observer is running, is 56 56,304. And remember earlier in my notebook, I grabbed the process ID of the .NET host that's actually running this thing. Different number, 57848, as opposed to 56304. Let's just run this cell one more time to make sure it's still the same process ID. Yes, 57848. This is what we expect, right? This is just a client process connecting to the service in running in our hosted Reactor. So that means if I kill off this notebook, my query will continue to run. So I'm just going to bring back in Task Manager here. That is, let me move this on top actually, so it doesn't submarine when I move the focus somewhere else. So where is it? It is 57848. That is our .NET interactive host process. When I close this notebook and say don't save, you should see that process. You should see that process go away. Well, that's interesting. Normally it goes away at this point. I am going to close the entire notebook process. Huh. That was, oh, is it finally gone? Yeah, that took its time. It's gone now. It was 5.7 something. There's nothing 5.7 in there at all. Okay, so it has eventually gone. But if I come back into Visual Studio, you can see, if I scroll to the top, this thing should still be, unless my collector has crashed. Oh no, there it is, still going. Right, so that's the new data. Yes, this is merrily churning away with new data coming out from the source. So this has survived the killing of the client process. And I'm just doing that to demonstrate that this is running out of process now. So the lifetime of my query is now completely detached from the lifetime of the process that actually defined and kicked off the query. This, by the way, is why subscriptions have GUIDs. It's URIs. It's so you can go and find them again later and tear them down again. Now, the next thing I want to do is demonstrate the persistence. So if I grab another one of these, oh, you've got to be very precise. Oh, hang on. It's doing a checkpoint now, which when you've got the debugger attached is not the fastest thing in the world. Okay, it's back up again now. Right, so let me go back into Visual Paint. So still running in process of the 56304. The next thing I want to do is give it a kick and see if I can make something fall over so I can demonstrate to you the robustness, the fact that if you lose bits of your infrastructure, the query will survive. So let's go and find that somewhere around. I've got a web browser. Where did it go? That's the one. So this is the Service Fabric Explorer for my local debug Service Fabric cluster. So if I look in this, I've only got, I've got my integration test running. Let's ignore that. I've got one instance of our Reactor service running, and I've deliberately trimmed this down for demo purposes. We have exactly one query engine host. Normally you have lots of these. Typically you'd have a compute farm. So this is emulating a 5-node compute farm. Microsoft often runs with way more than that. Yeah, you can have tens or even hundreds in a farm, and each individual compute node, each individual VM itself could well have several query engines running on it. So normally you'd have hundreds of these things, but because I wanted it to be nice and easy to find the right one in the demo, I've configured this to have just the one. So that's slightly artificial, but it works for demo purposes. So if I go into this, you can see, although there's logically one instance of this, let me just crank things up a little bit, you can see that Service Fabric is actually running 3 copies of it. So there are 3 replicas of my query engine host, which is the thing hosting this running query. So it's got a primary running on node 0, and it keeps a couple more nodes on standby. So if anything wrong happens, if anything occurs to node 0, then these 2 are ready to leap into action and pick up from where this thing left off. So if I come in to the list of nodes and just say to node 0, I'm just going to restart this node. Now, before I do that, just to remind you, the process ID is 56304. So I'm now going to restart node 0. Are you sure? Yes, I'm sure. And then, so when it next, if I just refresh it, I caught it in the middle of reconfiguring. So node 0 has actually already gone down and come back, but it's no longer the primary. It's now saying, okay, I'm in the process of making node 2 the new primary. And now that, if I refresh again, that is now where my query is hosted. If I come back into Visual Studio, it's mid checkpoint again, but once it's, there we go, it's running again. You can see my query is still running, and you can see that the names are coming through nice and quickly. Critically, it hasn't reset it to that state where it didn't know any of the names. We haven't gone into that state where it's gradually having to accrete all the names and all the combined latest have to sort of wait for that to happen. It's carried on from where it picked up. But if I look at one of these, if I quickly grab one on the clipboard again, I'm going to fire up a second copy of Paint so we can have both of them visible. Right, so if I get the old Paint, so we were in 56304, and if I can find my mouse pointer, here's the new one. This is in 26584. So we've changed to a different process. And if this was actually up on Service Fabric in Azure, then it would be on a completely different machine. Obviously, this is a local emulator, so all 5 nodes are actually running on the same physical hardware. But if you run it on a real Service Fabric cluster, then that would have successfully moved from one physical node to another. So that demonstrates the failover stuff. So that is essentially the end of that demo. But the next thing I would like to now show you is some of the actual real Reactor repo, because that is essentially what we're here to talk about, is the fact that this code is now out there. So here I have on my local disk a clone of the Reactor repo. And it's relatively easy to start looking at this. There's just one SLN file in the root, and if you double click that, it will open Visual Studio, and it will then take a little while, even longer than normal, take a little while because there are quite a few projects. Loading project 0 of 166. This isn't exactly the slowest of machines, but even this takes a little while to open things up. So once Visual Studio comes back to life, I will be able to start. Let's just ignore that for now. That would just be something shutting down. We can ignore it. Right, so this is the Reactor repo open in Visual Studio. I am going to attempt to zoom in, and I hope this works. It doesn't always get on very well with with Zoom. I am hoping you can see my Solution Explorer at this point. Can someone tell me yes or no? Can you see my Solution Explorer?
Yep.
Great, fantastic. So this shows the top level structure that Carmel was talking about earlier. We have Nucleon is all the low-level pieces, and let me show you an example of what is in there. So one of the things in here is support for Bonsai. So remember, Bonsai is the thing that is able to take .NET expression trees and send them across the network, basically serialize an expression tree and deserialize it somewhere else. That's not a thing expression trees know how to do by themselves, so that's one of the things that lives in here. And there's a lot, the data model thing that you saw earlier where I was annotating things with attributes to enable kind of structural typing, that's in here as well. So low-level stuff like that you don't necessarily have to be using Reactor for lives in there. And then we've got Reactive, which is essentially the Reactor flavored version of Rx. So if I look in the reactive.link project, you can find things like the implementation of all the standard link operators. So there's the group by operator I was using earlier. So if you are interested in seeing how that's implemented, you can just open it up. And there it is. So you can all now fully understand from that brief glimpse of a corner of my screen how that works. I'm not going to go into that one, but that's the real implementation that we were relying on. But the thing I was going to show you is how to get started with the demo. So if I go into the Reactor piece, so this is the building the actual service that's able to support long-running, persistent, reliable subscriptions. That's what Reactor builds on top of the basic facilities of reactors. So in here, you'll find things like the query engine and a bunch of kind of remoting support and metadata services, everything you need to be able to build a complete service, and also all the client-side pieces that you will need to talk to it. So the client context stuff that I was showing you in the notebook will essentially come from here. In addition to this, there's also a samples folder. And this is where you could look if you wanted to actually start running things out of this repo. In particular, you want to look in this weirdly named folder here, shebang. What on earth is that name about? So that is shebang as in the phrase, the whole shebang. So what does that mean? In order to host the query engine, you need to provide it with a bunch of services. It needs to have access to some sort of persistence engine so that it is able to generate checkpoints. It needs access to a metadata service so that it can keep track of subscriptions and their characteristics. It also needs to be told which particular operators you want to load. Because actually something I haven't mentioned yet is the raw query engine essentially doesn't know anything other than very, very basic RX. The only things it really understands are observables, observers, and subjects, and a couple of other related ideas. It doesn't have any built-in operators at all. All of the operators that I have used here have actually come out of the reactive piece here, and if you want those available in your query engine, you have to tell it that you want them available in your query engine, all of which means that if you want to run anything out of this repo, you have a heck of a lot of setup work to do before you can get anything that does anything even slightly useful. So the purpose of the shebang libraries is to give you a starting point. The shebang libraries basically get you up and running. They get you up to speed quickly. The main library you want is this shebang.app. And you'll notice in here, there are a couple of notebooks. So what I'm now going to do, I'm going to turn off the magnifier. I'm going to come out of here. Let's quit that. And I'm going to open this up in File Explorer. That's the word I'm looking for. Where's it gone? Under the mouse pointer. Right. I'm going to open this up in Visual Studio Code and open yet another AIS demo. So, I've scrolled to the bottom of the file. Let me go back up to the top. Right. So this is Bart de Smet's version of our AIS demo. So Bart de Smet, remember, is the brains behind Reactor. He's the guy sort of who basically made it all happen, him and his team. And he took our AIS demo and did his own version of it. And it's slightly different from the way we approach it. This basically has all of the working parts kind of hanging out. All the guts are hanging out. You can see how everything works, which if you want to get a thorough understanding of exactly what Reactor is doing for you, is great. And if you just wanted to get a demo up and running, makes it surprisingly hard to follow. But I am now going to give you a quick tour through it so you can see what's in here. Now, the first thing to understand is that none of this will work if you haven't already built this project here. I have already built this, which is good because it takes quite a long time to build. So it assumes you've built this in debug mode because it's going to refer to components that are in here. So that's a prerequisite. It's also using the same AIS.NET libraries that we had earlier. So I need to run that. That's going a bit blinky, isn't it? Hopefully it will. There we go, we're done. Right. So then he uses the same receiver host that we've written. Bart tends to package things up slightly different. He does everything in terms of method calls, which he then invokes right at the end when he's ready to go. Oop. No, I do not want Visual Studio to try and build all of Reactor at this point in the demo. Thank you. Right, so we run this. This is the same sort of Bing Maps, JavaScript command handling stuff you saw earlier. This is just how we get messages from the C# code into the Bing Maps code. This is the Bing Map. If I scroll down, you should see the same thing before. There's Norway. So then things look a bit different. So here, this demo loads the shebang app. So this is why you need the thing to have been built. And then we have a bunch of helpers that kind of spin up an entire world of local query engine. So the first AIS demo I showed you was just using plain RX, so it didn't have to do anything. And then the demo I did just now was using Engine's hosted Reactor as a service system. So none of this was your problem. You just needed to get hold of a client connection to our service and use it. But this, the purpose of this notebook that is in the repo inside the Shebang app folder, the purpose of this demo is to show you what it takes at a bare minimum to create a new query engine, sorry. Well, you call query engine factory.create new. Simple. But also this has to deal with things like providing somewhere to put the checkpoints. It has to deal with the slightly knotty problem of how do you get data from outside Reactor into the query engine? How do you get the events that the query engine has produced back out again? These are all things that I hid away in the last demo by just having these neat little things you could point at an event hub. But here, all the guts are kind of hanging out, and you have to see how it, and the way it works is visible. So he's got this ingress egress manager thing going on. So Bart's written these helper functions that let you run some piece of code. You get to pass in a function that it will invoke, passing in a client context, which remember is the way you talk to a query engine, and it will invoke your function having spun up an in-process query engine. So this one, with new engine, creates a brand new engine, invokes your action, passing in the context from that engine, and then when you're done, generates a checkpoint and unloads the engine. So that's what this one does. The second function with existing engine is almost identical. Takes a store, ingress, egress, your function. But this one, rather than building a brand new query engine, says, I believe I am recovering from a checkpoint. So I'd like to use the checkpoint that's in this store to recover the last known state of the query engine. So this will actually recover whatever state it was saved into the store. And then everything else is basically the same. So this gives us either a brand new start or a continue from where we left off option. So let me run this so those functions are available. And then we scroll down. So here is just checking that all works. So here we're actually going to use the with new engine thing. We're going to provide an in-memory store, a magical thing called an ingress egress manager that we'll get to in just a minute that handles input and output. And this then invokes this function, which is going to create a timer and allow it to run for 5 seconds. So when we run this, we can see it creates the engine, creates a trivial subscription, and you can see the timer events are coming out there. And then it shuts down, unloads the engine, and away we go. And the reason all the guts are hanging out is because you can then do things like invoke this method that actually saves the checkpoint out to disk. So in principle, we could go and look at this. I won't be able to tell you much about what it means, but I can just show it to you if you're curious. In this demo, he happens to use XML as the persistence format for checkpoints, which is perhaps not optimal, but that's just how the demo works. It's not how real implementations do it. Interestingly, all of the standard operators actually end up in here as objects in their own right. So we'll scan past those. But this, one of these is the subscription we just, they're both of these are subscription. These are two different aspects of the same subscription that we just created. And this will be a base64 blob containing all the information about, I think, how that subscription is defined. And this one contains all of the state in that subscription. So that's essentially how many ticks has the timer generated so far. I'm not going to try and decode that. Anyway, so that's what checkpoints look like in this demo. In real applications, they are a bit more compact. So then, once we've got that, we can load that file back off disk back into a brand new in-memory key value store. So we're going to load that state back in, and then we're going to use the other helper to say, I've got a store that's got a checkpoint in it. So I'd like to build an engine based on that checkpointed state. So when we run this one, it picks up from where it left off. Now, for various reasons, the timer tick outputs are going into a console.out that no one can see. So there's nothing actually to see here, but take my word for it, it is actually running. So, having got ourselves the ability to spin up an entire query engine, now we can start trying to process AIS messages with it. So, we are going to, for some reason, he then does a bit more of the hookup with the client-side code here. So we find the JavaScript kernel so that we'll be able to send messages to the map. Then we do this sort of data model thing. Bart's one's more complex than mine because he does some of his demos do more processing, but basically this is the same thing where we're saying, okay, we're going to need to work with the longitude, latitude, and all this sort of stuff. So again, remember the point of this is so that these types don't have to exist inside the query engine. These get turned into structural types with just these names here to represent the properties. So with that available, then we're going to carry on hooking stuff up to the JavaScript code. So we define the custom command we're going to pass out to JavaScript land. This is exactly the same code as you saw in my earlier demo. Then Bart does something slightly different. He actually sets up an observer so he can hook things directly into the map through Rx. So if you have an observable source of kernel commands, you can plug it into this and it will send those up to JavaScript, which is very nifty. Now, we're going to build another query engine, but this one is actually going to be processing real AIS messages, which means we need somehow to get those messages in to the query engine. And this is where this ingress egress manager comes in. This deals with the kind of boundaries around the edge of a query engine. It enables us to open up little pipes into and out of the query engine. And you do that by actually creating Rx subject objects. So this is saying I'm going to create two subjects. And at this point, the ingress egress manager neither knows nor cares whether these are inputs or outputs. But as it happens, we're going to have an input called AIS data and an output called vessel positions. And so we tell the ingress egress manager, okay, we're going to need a couple of ports to get information in and out of our query engine. So please create those for me and give me Rx representations of those so I can then plumb data in and out. So these things now that gives me a way of feeding data in to the query engine, and that gives me a way of extracting information back out again. Then Bart's demo just does some tracking. I'm not going to talk about that. But here is where we start actually processing the AIS messages. Now, Bart does a bit of massaging on his. Our data source provides multiple different implementations of this AIS message type. Bart, for various reasons, wanted to flatten this down into a sequence where every object in the sequence had exactly the same concrete type. So this is essentially flattening all the different message types we support back out into one size fits all message type, just because that was convenient for how his demo worked. And then this thing talks to the receiver host, and this is where we connect the receiver host that goes and talks to the Norwegian server, connects that up to the port that we created for feeding data into our query engine. So basically this is going to read data from Norway and push it into the query engine, making that data available for queries that run inside of the engine. Why didn't you see any of this in the last demo I did? Because we hide all of this for you in our hosted Reactor implementation. So you don't need to see all this sort of stuff. We're doing all of this under the covers, but now, because the way this demo is structured, it's all the guts are hanging out. This is just some statistics tracking to check it's all working, and this is actually kicking off the receiver, and it basically returns an object which, when you dispose it, shuts everything back down again. So that gives us the ability to basically feed data into the engine. And now what about the output side? How are we going to do the other side of it where data comes out of the engine and into our map? Well, here, this method here is going to grab the JavaScript kernel, get hold of that outbound port. Remember, we used the ingress egress manager to create a couple of ports for getting data in and out of the Reactor query engine. This is the outbound one. And we're saying whenever something comes out on this port, we're going to plumb that into the kernel command observer that, remember, sends stuff off to the map. So this is basically, say, things coming out of this port on the edge of our query engine are eventually going to be fed into the JavaScript map code. So let's run that. So now we should be ready to actually run the query. So we're going to define a subscription URI, and we're creating a brand new engine. So we're going to have a brand new key store to hold the checkpointing states. Here, we're getting hold of the iasync reactive observable and iasync reactive observer that correspond to the input and output ports that we created. So remember, the AIS data is the way we can feed messages in from the outside. Well, this method here gets us an object that represents that source, but from the point of view of the inside of the query engine. So this, if it will show me, is an iasync reactive observable of AAS messages. So this is the thing that lets us, this is basically the thing I more or less began with in my previous demo. And this is the observer that's going to push stuff out. And again, now, this should look rather familiar by now. Group our vessels by MMSI, and within each group, find the navigation messages, find the name messages, use combine latest to combine the latest name with the latest navigation data for each vessel stream, and flatten that back out into a linear stream of vessel positions, reporting the position, course over ground, vessel ID, and name. So this, when we actually subscribe, we're going to subscribe to that and hook that up to the sync. This will cause data to flow through the query engine. So we run this and it creates the engine. It invokes our code. It creates a subscription and immediately shuts down, because this method, no sooner is it subscribed than it returns, so it doesn't run for long enough to do anything. So we've got our subscription now, and then we immediately shut the engine down. So we now have a checkpoint that contains that. So that wasn't very interesting. But now we can load that back up again. I mean, Bart could have left it running, but he chose not to. He was showing off. He wanted to show that it was able to checkpoint all of that. And then this says, okay, now I'm going to load an engine from the checkpoint that I know is in there. And then we're actually going to call the outside world methods that kick off the actual work. So at this point we're saying, okay, please start actually running the receiver to make it all happen. So when I run this one, we see events are being processed. If I quickly scroll up to where the map is, hey, ships start to appear. There we go. So look, it's real. And then immediately stop, because none of these things in Bart's notebook ever run for longer than 5 seconds. But hey, we've got some ships. And then if I go back to where we were, so you can see it will shut down again, and you can checkpoint again, and then load that back in. So this sort of simulates what would happen if your server shut down or you migrated the subscription to a different server, where you're going to load the persisted checkpoint back into memory, and once again start the engine up from that store, but potentially on a different machine this time. And we run again, and the engine recovers its checkpointed state and continues to run. So if I come back up to the map, oops, I've overshot, we start to see more ships moving around, and so on. And then within a few seconds it shuts down again, because that's what this notebook does. Whew. And I think that is everything. Oh, and one last checkpoint, though. We can save it out one more time. So that is the version of the AS demo that you can actually run, because that's actually in the repo. So we're almost done. I got one last set of things I would like to talk about, because people often ask this question: what else is there that's a bit like Reactor that's out there? Because this sort of thing, this processing of events, Reactor is not the only thing that does it. And so it's interesting to ask, what else is like it, and in what ways, perhaps more importantly, does Reactor differ from some of the services that are out there? So I'm not going to go into a huge amount of detail here. This is more of just a very quick survey to give you a rough idea, but it's we'll go over it quickly. So here are a few of the obvious alternatives if this is the sort of computation that you're doing. So there are a whole bunch of things that the Apache Foundation offer. So there's Apache Spark. Some people do direct raw processing of event-based computations directly on top of Spark. Now, that is somewhat hard work, because you end up doing quite a lot of work to actually enable that. Out of the box, most of the things that host Spark make it a bit easier to work with files and things like data lakes. If you want to do event processing, you often have to do a little bit more work to hook that up. However, they have various things that can sit on top of Spark for you, things like Storm and Flink and Samza, which give you varying levels of abstraction on top of the Spark cluster for doing event-based processing. So those things on the left there are all sort of Spark-based. There's also CIDI, which is another Java-based thing. I would say that's actually possibly the thing that is most like Reactor in here, and I'll explain why that is over the next few slides. There's also some things in the kind of Microsoft world as well. So there's Azure Stream Analytics is more or less exactly in this sort of space. It's a hosted service. There's also actor model type systems like Akka.net and Orleans. So let's talk about how you might compare these and contrast them with Reactor. there's various dimensions you could sort of split it along, and one obvious one is what's the technology stack you're sort of buying into if you want to use this technology. So all the stuff on the Apache side and also the CIDI stack, they're all based on the JVM. So you're going to be writing either Java or some sort of JVM-based language such as Scala or maybe Clojure if you want to extend these things. Now with Apache Spark, often people control it from Python or even C#, other languages, so you don't necessarily have to be using the Java well, but the fact that it's all implemented in Java under the covers does tend to become apparent the moment you do anything other than fairly vanilla stuff with it. So you're essentially in a world of Java there, and since this is a .NET user group, that might not be hugely appealing, or maybe it is, I don't know. So that's one way of looking at this, whereas the stuff on the right is much more in the Microsoft world. So Akka.NET, that's a .NET-based thing. Orleans, that's a .NET-based thing. Stream Analytics, that's a bit more complicated. If you run it in its edge mode, where it's actually running on devices, that is .NET-based. If you want to extend it in the server, you're actually using JavaScript there. So depending on which bit you're doing, it's either JavaScript-based or .NET-based. So that's one way. What sort of world of tech are you in with this? This says nothing about how any of them work. It's just sort of what sort of technology familiarity do you need to understand how these things are working. So another way you might look at it is to say, what is the computation model that these things use? And using a very broad brushstroke, you could say that there are the actor models and there's everything else. Now that's possibly a slight oversimplification, but it's not without its truth. So Project Orleans and Akka.NET are essentially based on the actor model. The Orleans team would sort of dispute that. They studiously avoid calling themselves the actor model because it's contentious, but it's something that resembles it, even if it isn't strictly the actor model. And the thing with that is that you get a very kind of well-defined environment for processing messages that flow through the system. You basically get a great deal of environment-supplied control over the order in which things happen, but the actual application logic is basically just code. If you want to do some work, you write some .NET code that runs inside one of these things. They give you all sorts of guarantees about how and when that will happen and what the robustness is around it, but fundamentally, your actual logic is going to be expressed in some sort of .NET language that is hosted by these things, roughly speaking. Whereas all the others have some sort of formal model. And in the case of most of the Apache stuff, it looks quite a lot like database tables of one kind or another. So particularly in the Apache Spark world, people often tend to be processing tabular data of one kind or another. Now, it's not quite the relational model because you have a bunch of things like, well, there's all sorts of reasons it's not quite strictly that model, but it looks and feels, if you squint and blur your eyes a bit, it all looks like database tables, even the event-based stuff. This is the thing. If you look at the way the event-based things are handled, they tend to look a lot like a table where just one row gets fired at you at a time through the system in a sort of sequential fashion. That is an oversimplification, but it gives you a flavor of what they're like. And the critical thing is the way you define the behavior in these things is not through writing code that's going to run and do the computation most of the time, although there are user-defined functions, but that complicates matters. Most of the heavy lifting tends to be done by applying built-in operators over the data. So you would tell it, I want you to group like this and then combine like that, and someone exactly like we were doing in RX. And then the advantage of that is that these systems can understand what it is you're doing. So whereas the actor things don't really know what the code you've given them to run does, these things that have a formal computation model and well-defined operators can actually understand what you're doing, and that gives them the opportunity to modify how things run. They can build execution plans, or they can decide to restructure your query so that it can be parallelized across a large number of machines. And so that is an advantage of that formal model. Now, where does Reactor fit into this? I didn't mention Reactor on the previous slide. I hope it's fairly obvious that it's based in .NET now, if I didn't mention that. It's definitely a .NET library. Although, the Bonsai tree format is actually by design language independent, and Microsoft have not released the code for, but have written implementations in JavaScript and C++ as well. So it has the potential to be cross-platform, but the actual code you can get hold of today is all .NET. In this model, Audience and Akka.NET obviously are running .NET code. Reactor's model is interesting. It is a formal model that is subject to analysis, and one of the ways that Reactor is able to deliver the massive scale that it can is in exactly the same way that these systems like Spark are able to. They can reason over what it is that your queries are doing and restructure them and distribute them across the compute farm in the optimal way to take advantage of the compute resources that are available. And this is made possible by the fact that there is a formal model. However, one of the big differences with Reactor is the formal model is not set in stone. If you look at something like CIDI, which for reasons I'm about to go into, is probably the most similar of these things to how Reactor is built. CIDI has certain concepts that are baked in at quite a low level. So it has a notion of aggregation. It has a notion of windowing. It has a notion of filtering and projection. These things are stuff that it just knows how to do and which are a fundamental part of the formal model that it uses. Reactor's not like that. As I said earlier, when you create a query engine, it doesn't know how to do anything other than the most basic RX type operations. It knows what observables and observers and subjects are. It doesn't know what filtering is. It doesn't know what grouping is. It doesn't have any of these things built in. You have to install those operators into the engine, which means you can extend the set of operators. So for one application we built with in Engine for Reactor, we ended up building our own custom operator because it was a more efficient way of achieving what we wanted than getting the same effect by composing the built-in ones. So you can do that. But then that raises the question, well, if I can write my own code and define my own models, how on earth does the optimization work? Well, the answer there is there's a piece of Reactor I hadn't really talked about called the query coordinator, which is customizable. So you can actually extend, well, you can build your own smarts into your query coordinator. So if you have your own custom operator, you can build your own corresponding optimization logic for it. So it has an extensible model with formal underpinnings that are based on RX. So that's what makes RX, one of the things that makes RX sort of different from all of these things. It has a lot of the benefits of not being tied to one fixed model while still gaining a lot of the benefits that are available from a formal model. And one last thing to talk about is to ask, how can we reuse these things? Most of the things on this page are designed to essentially be a world that your code runs in, more or less. So the assumption is Akka.NET is going to provide an environment that deigns to run your code, or you'll have an Apache Spark cluster probably hosted either in Azure or through some Databricks provider or whatever, and it will host your code. So if you want to do something like run it on a Raspberry Pi, it's quite challenging because you've got to create a full runtime environment there. Whereas Reactor and also CIDI, and this is why I say CIDI is probably the most similar to Reactor, they are ultimately a bunch of libraries. And you can pick and choose which bits you want to use. And if you want to, you can just use them like any other .NET library, or in the case of CIDI, like any other Java library. You can just load them up and start invoking methods on them, give them what they need to run, and then a little bit of sort of hosting context. But once you've given them what they need, you can just run them in memory. And this means that it is possible to use them on big compute clusters in highly parallel environments, and it is also possible to use them out on the edge on relatively constrained devices such as Raspberry Pis. And so that is another of the things that's sort of where Reactor sits on this diagram. It's like a bit like CIDI in that respect, but unlike all the other things. And so that, I think, is the last dimension I am comparing things on. So with that, I am going to hand back to Carmel to wrap up.
Oh, phew. Okay.
If you're all still awake.
Right, so we're keeping you all from the virtual pub here. So Yeah, we've seen that Reactor extends classic RX by adding the ability to support long-running and stateful queries. It allows us to process a huge number of events every second over a period of years, and through this persistence and reliability, we can support planned maintenance, migrations, and even completely unpredictable failures. The examples we've shown were mainly around vessel tracking, but the long-running and high-throughput processing allows us to support a huge range of really complex, big data scenarios, most of which we have not even thought of yet. And so lastly, I guess it's just the question of what now? So you may have seen on my very quick run through the site earlier that there was a tab, Contribute. So there are loads of ways you can get involved. You can start the repo on GitHub, which just lets us track how many people are interested in the project. You can help spread the word. You can do this by blogging, creating videos, talking about it at your .NET or other user group. You can submit actual contributions to the repo, so those could be documentation, samples, demos, or actual updates to the code base. There's a load of issues on the code base, which are a good place to start. Or you could, you or your employer could sponsor the project. So yeah, there's also a, you can see at the top of here, there's a Slack channel, Slack workspace, and there's also a Twitter account, which the link is here. So yeah, just finally, thank you all for listening. There's a lot of useful links here. I've got the Reactor.net site, the GitHub repo, the endjin site if you want to know more about us, the Reactive Twitter account, and mine and Ian's Twitter. So yeah, finally, just thank you all for listening, and I hope you enjoyed it. If you have any questions, then happy to answer. But yeah.
Yeah, thanks very much, everyone.